So this is what the formulation looks like, but it's in some sense not as nice as the classical one because of this fact that this lives in some K1 torsor rather than an honest element in the field of fraction or the ring of fractions of lambda g. But this is more general, so this applies in any situation, and this is what Fukai and Kato call equivariant Tamagawa number conjectures with this in that paper. So, but in this case, we can get an honest element of field of fractions of lambda g. So whatever I said up to now more or less works. It's certain slight modifications for any t and any extension. Okay, so you have to take care of the Archimedean places and so on, but it works more or less for anything. Now, the next thing I'm going to say is very specific to this situation. So, we can get an element we can get an element of the total ring of fractions of lambda g from L as follows. So now here I'm going to use the fact that G is of this very specific, G is of this form and then it's commutative and so on. So here Q lambda G tensored over lambda G R gamma, so this C is acyclic. Okay, so there exists a canonical, so there exists this canonical map from determinant of Q lambda G to, so this, let me call this CQ to determinant of Q lambda G of 0. So I can compose my, so L Q lambda G. So let me write it like this. So this from determinant of Q lambda G 0 to determinant of Q lambda G 0, and now this will live inside Q lambda G. Okay. Which is just the total ring, which is just the units in this. So the main conjecture in this situation says that there exists this L in Q lambda G cross, which is related to. So I just related to L values, and this thing here is the class in this relative K group. Okay, so remember that this boundary map was just a map between K1 of Q lambda G to K0 lambda G. Okay, and C is the class in here. So this equality. So we can formulate either this main conjecture very generally with elements in K1 torsor, but sometimes we have this property that when you localize at certain subset of lambda G, we get acyclicity, and in that case we can get an honest element of that localized ring. So that this is probably the point of view closest to what Wing Young was talking about, and probably what Malta Witter will talk about. Okay, so let's stop.
the intervals of the complex, once you tensor the fraction field is classically.
Yeah.
There's nothing on the ring that there's no condition on the ring to impose.
No, so I mean, as long as sort of these things hold. So if you have a non-commutative ring, then I think the total ring of fractions still exists, but it's not so. I mean, these kind of things won't be so nice. So that's why you have to take some other localizations. Yeah, I mean, as long as this holds, there is nothing else.
I guess typically you need some conjecture that the complexes of interest have this property or something.
The complexes of interest have these properties, but if I take a more general thing here and just define the naive thing that I had up there, even with the modifications that Archimedean places, these conjectures will not be true. I mean, these things will not be true. So you have to carefully choose your local conditions for such things to be true.
How does mu equal 0 enter into this? Is there something about finite perspective dimension that's important? If mu weren't 0?
So mu equal to 0 enters here because I mean, if you so in the formulation it doesn't enter at all. That's why I did not say anything about mu equal to 0. But when you try to prove this, the only sort of, I mean, when G is abelian, the only way we know is sort of to prove such a thing character-wise. And then when you want to put it together, so if you want to go from character-wise back to the group ring, then there could be some denominator, right? And the fact that mu is 0 is precisely the thing when you don't. I mean, no, sorry, not precisely, but if mu is 0, then you can show that these denominators don't appear.
So as far as the Fukaya-Kato formulation goes, mu equals 0 isn't really important.
It's not
You
important.
never
No.
did anything.
And also in the previous formulation that I had, without this condition, even these sort of these conjectures can be very hard to prove. So even that is not necessary in some sense, but then you don't get an honest element in some ring that you would like to have.
Oh, sorry, could you say again where the mu equals 0 comes in?
So it doesn't come into the formulation, but if I want to prove such a statement, so presently the only way to prove, we know how to prove this is to prove such a statement. So if my G is delta cross gamma, then I prove it for each I compose with characters of delta, and then I prove the statement, these kind of statements character-wise, and then I want to go back to the Iwasawa algebra of this, but that introduces some denominators, and then you can get rid of the denominators if mu is 0.
And the mu equals 0 conjecture, the relevant complex is this one in that case, right?
The relevant, yes.
Is it easy to explain what this has to do with Tamagawa numbers? Is that something?
No, I think from. I mean, at least it's not easy for me to explain. And these elements are in some sense of some volume. They are computing volumes.
More questions?
Yes.
There's a notion of white erosion generally the notion of fortune. Investigator Milner and the work is somehow relation.
So is that what? Sorry, I'm very ignorant. So is that SK1 or something? The white torsion?
What's that GL?
Yeah.
The GL lambda thing you wrote down.
Right.
It was there, and then it's sort of a general description of how you group the object together, and so then you can actually reduce it in a chain complex and evaluate and get the Reidemeister torsion. It's like a global Reidemeister torsion.
Okay, I don't know this.
Some invariants which you can also use if you have asymmetry complexes. It's a secondary variant. Surely I think
Must be
very
that way.
similar.
Okay, I don't know.
Mm,
Sorry.
I never thought about this carefully, but I suspect the torsion in that sense of these complexes is related to the Tamagawa number, right? Or P components of this P part of the L value, or something, of the rational part of the L.
Sorry, I don't know that.
More questions? Thanks, speaker again.